Where did we stop?
Fractional sterilization.
Okay. Sterilization. All right. Any questions? No? Chapter 7, which we hope I'm going to finish today, or almost finish. No? Physical factors of control. We are done with temperature. No, not quite done. Moist heat we are talking about, right? The last of the moist heat is fractional sterilization or tendilization. Yep. Still booting up. Okay. Thank you. Excuse me. Tendilization or fractional sterilization. If you remember John Tyndall, right? Who came up to the rescue of Louis Pasteur, okay? Who resolved the idea of spontaneous generation. John Tyndall is the one who introduced us to the idea that bacteria exist in two forms, vegetative form and endospores. Then he also came up with the idea how to destroy endospores. And this is how he came up with the idea of tendilization. And this is especially for these type of liquids, heat labile or heat sensitive liquids, especially for those materials or liquids especially that are heat sensitive. Heat sensitive liquids or heat labile material is defined as any liquid that cannot be heated over 100 degrees. That is heat sensitive material. So this is a process, tendilization is a process in which you heat sensitive material between 80 and 100 degrees for 30 to 60 minutes on each 3 of the successive days with incubation periods in between. Let me just draw you a diagram to explain. Oops, where's what happened to his? Okay, we'll talk about dry heat in a minute. This is Mr. or I don't know if he's Dr. Tyndall, but that's his picture. Dr. John Tyndall. Yes. So let's look at his experimentation. One of the media that we use in microbiology lab that is heat sensitive, you cannot put it in the autoclave. By the way, all of the media that we use in our lab is heat resistant. We can sterilize it by putting it in the autoclave. One of the media that I used to use in the past is urea broth. Urea broth. I've not used it in a long time. Okay. It is heat sensitive. Okay. So how do we sterilize it? Okay. Nowadays there are better techniques. Okay. The best way to sterilize it is filtration. Okay. But in his days there were no membrane filters available. So he came up with this idea. Urea broth is an excellent medium for the diagnosis of H. pylori. H. pylori. Okay. The original color of this medium is peach, beautiful peach color. Okay. Confirmation test for this is doctors, when they do biopsy of a person who has peptic ulcer, they do biopsy, they take the tissue of the stomach and they put it in this medium, and the color of this, within about 12 hours, the color turns hot pink. Okay, so that's the confirmation test. All right. So let's say you have broth in a flask contaminated with endospores and vegetative cells, and you want to sterilize it. Okay, so you on the first day of sterilization, you start to heat your broth 80 to 100 degrees. How long? 30 to 60 minutes. What would this do? Kill off any vegetative cell that may be present. Then you do what? Incubate. 37 degrees for 24 hours. What will that do?
Allow the endospores
to germinate. Allow the endospores to germinate. So endospore will germinate, and then you repeat the process of heating the second day. They didn't have TVs and Nintendos and all that. They had time. Okay. So that's why they came up with all these good ideas. But now we have lasers and all that to zap, zap, zap. Quick, quick, quick. Everything is quick. So second day, if there were any endospores left, they would have germinated. So he heated it again, second day. What happened to my, oh yeah, 80 to 100 degrees, 30 to 60 minutes. One last incubation. Come on, let's put this away. If there are any endospores left, they will germinate and they will become vegetative cells. And one last heating. I don't know why the size of my flask is shrinking. "30 to 60 minutes, and you have what? Sterile urea broth. Last time I asked you a question, is there such a thing like partial sterilization? No. Don't get confused on the test between fractional sterilization and partial sterilization. This is fractional sterilization in portions, step by step. But this is not partial sterilization. It does accomplish sterilization, but in fractions, portions, steps. Okay? So it does. Tenderlization is fractional sterilization. Okay? So this is the last type of moist heat. Moist heat. First one was autoclave. Second was boiling. Okay. Third was subboiling, right? Pasteurization. Mm-hmm. Oh, sorry. You're right. Yeah. Thank you, Beverly. So which two methods, moist heat methods, they accomplish sterilization? Which two moist heat methods accomplish sterilization? Autoclave and endolyzation. Boiling doesn't. Pasteurization doesn't. Okay, right? What else did we talk about moist heat? That's about it, right? Okay. Dry heat now. Move my, sorry, backwards, previous. Come on. Okay. Dry heat, not everything can be placed in autoclave. Like oils, you cannot. Powders, you cannot. So anything that you cannot put in the autoclave, you can sterilize it by putting in the hot air oven. The problem is it takes too long. Remember the example from last time? You can kill the endospores of Bacillus anthracis by putting in the boiling water within 2 to 15 minutes, 100 degrees. Same endospores in the hot air oven, how long? 3 hours and 140 degrees, much longer. Okay. So hot air ovens, they do accomplish sterilization. Hot air ovens do accomplish sterilization, but they take much longer. Okay. Incineration, burning. This is another way you can accomplish sterilization. When you flame your loop in the lab, you accomplish sterilization. This is the only way you can sterilize a human. Okay? Yeah, really. Yeah. Low temperatures now. Always, always static, never sterilant. Okay. The purpose of low temperature is to preserve your material. They never accomplish sterilization when you put your food or any other specimen. Okay. Embryos, tissue cultures, okay, or Walt Disney, Mr. Disney is being preserved. Okay. his whole body is being preserved in the hope that someday he will come back to life. There's a good chance that he will come back to life. There's a very good chance. Yeah, 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 yeah. But the science is so advanced that your body does not need to be preserved. You can be cloned. Your whole body can be cloned from one somatic cell. They don't need your sperm or your egg to reproduce you. You can be cloned from one somatic cell. One somatic cell. The body is so advanced. I mean, the science is so advanced nowadays. But at that time, they did not know that. So he is being preserved where? Not in the backyard in his granddaughter or grandson's freezer. No, Why didn't he do that? So when I'm dead, just put me in the freezer in the backyard. No. What's the disadvantage of that? Not cold enough, and ice crystals. When you put something in the freezer, ice crystals are made and then they damage the material that is being preserved. That's why your food goes bad. Ice crystals are made and they literally damage, they puncture the material that is being frozen. Okay? That's called ice burn. Okay? So the best way to preserve the material is right here. If you want to preserve something for centuries, literally, right here, liquid nitrogen. This is nowadays, this is so common that even chefs, they use them for cooking. Okay? If you watch cooking shows, the biggest advantage of this is magicians use this right here. They put a rose in liquid nitrogen, they pull it out, crumble the rose right in front of your hand. Okay? Or they put some plastic, like ball or something in liquid nitrogen and smack it on the wall. Powder. Okay? We had a chemistry teacher who used to do a magic show. He used to do that. Tennis ball in the liquid nitrogen, bang on the wall. Okay?
So is that what he's being preserved in?
Right here. Right here. Exactly. Little flick. Yeah. Ice crystals. Ice crystals is permanent damage. You cannot recover that. Okay? He will be so ugly. Sorry. No, I mean, it's a permanent damage. But right here, when you're retrieved, you have to be there's a special process to recover, to retrieve embryos or tissue cultures, stem cells and everything. You have seen the CSIs and all that, and they pull something out from this cloud, liquid nitrogen. Okay, it's not that easy. It's just a special process of that. Yeah. Sorry. Come on. What am I doing? Here we go. So low temperatures, the purpose is preservation, not to destroy microorganism. All right? Okay, next. Come on. Desiccation. Again, you want to dry fruits, dry vegetables and all that. Are they dead? Microorganism dead? No. If you take the water away, like 80%, 85% of any microorganism, any cell is what? Water. You take the water out, what happens? What's the proper term for that cell? Microbe? Plasmolysed. The cells are plasmolysed, and that is static. Microbe is static. So you take the water out, the cell becomes inactive. Okay? You return the water, they become metabolically active. And that's how we get our cultures, desiccated form, powder form. Okay? Because it's not safe to transport the culture in liquid form, so we get our cultures in powder form, dried form. We get the culture, put broth in, they grow back. So desiccation is static, never sterilization. Come on. Okay. Do all microorganisms, they dry at the same rate? No. Remember, some microorganisms, they have capsule, some have mycolic acid, some they don't have cell wall. So desiccation, it will depend on what type of microorganism. And Desiccation also depends on where the microorganism is being dried, okay, on the environment, okay. What type of organism you are drying. Come on. Material in or on which organism is being dried. Are you drying your organism on a sheet of glass, or filter paper, or wood? Okay. Are you drying your organism? That always beats me. Dryness, completeness of drying process, of course. If you complete the process, it will be complete. If you don't complete it, it will not be complete. Next, physical condition involved, such as temperature and humidity. If the process is taking place in Florida as compared to Wyoming, which one will take longer? It's humid here as compared to Wyoming. So where would it take longer for you to dry your microorganism, here or in Wyoming? Right here, very humid. So it depends on the examples. If you have a roommate with gonorrhea, yeah, these are real life examples actually, okay. And this person pees all over the toilet seat, and they don't clean the toilet seat. And there are people really, I mean, believe me, I just came out of the faculty bathroom and just, and they don't wash their hands. And I feel like grabbing their neck and saying, what are you doing? Really? Faculty lounge. So I'm going to invent a big boxing glove and put it on top of the door. And as soon as the person leaves without washing their hands, going to smack them on their head. Really. There's a big sign there for your safety, and it says blah, 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 blah. That's why one of my goals is for that poster, to ask you to make those posters, to make faculty and everybody aware of these things. Really, that is my intention. What can I do really? So anyways, so this bacteria cannot survive on that toilet seat. Yeah. So if your roommate, if you don't use that toilet seat for a few hours, you are okay. People have sores on their butts, okay? If you use that toilet seat immediately, you don't know this person has gonorrhea. Good luck. All right.
So you said it'll die within a few hours after being dried.
Yes.
Is there
Very
anything,
sensitive.
What else can you use to kill it?
Lysol.
Lysol.
Lysol is very effective. Yep. Lysol even kills HIV. Yep. Mycobacteria. This bacteria can survive in the dried sputum for up to 12 months. You have seen people spit all the time. Now imagine a roommate who has TB. Just came to the United States from wherever, now has TB. Lucky you, your roommate. Okay, just spits on the wall all the time. Okay. Can survive in the dried sputum for up to 12 months. And then, endospores, they can survive thousands of years. So desiccation, dryness, depends on the type of microorganism. All right. What is this? Yeah, I should have moved it up, but this is the pressure cooker autoclave. Autoclave that accomplishes sterilization. This is where we bake our turkey during Thanksgiving in our department. Not, please, okay, no. Radiation, okay. I'm going to summarize this for you on the whiteboard for you. Radiation, what types of radiation? Some of you had in the other class, they had trouble understanding the words, so I'm going to summarize this. Radiations can be classified into two categories. Radiation. One, ionizing. Ionizing. Yep. Ionizing radiations, they have short wavelength. Short wavelength. The distance between, when they travel, the distance between the waves is short. Okay. The other one is non-ionizing. Non-ionizing. The distance between the waves is long. What does that have to do? Because this distance is inversely proportional to the amount of energy. This distance between the wave is inversely proportional. Short distance, more energy. Okay? The distance is inversely proportional. Less distance, distance between waves, more energy content. More energy content. Number two, more energy content means they can be used for what? Sterilization. Can be used for sterilization. Why? Because they have more penetrating power, more penetrating power. How do they accomplish sterilization? They not damage but destroy DNA. They destroy DNA. Destroy DNA. And then finally, examples: X-rays and gamma rays. X-rays, gamma rays. That's the summary of your ionizing radiation. Complete opposite of this, non-ionizing radiation. More distance, between waves, okay. Less energy content. Okay. Cannot be used for cannot for sterilization. So what are they good for if they cannot be used for sterilization? Disinfection only. And only for surface disinfection only, because they don't have penetrating power. Less penetrating power. Less penetrating power. What do they do to DNA? Not destroy. Damage DNA. How? Very good. By making thymine dimer. So, damage DNA. By making thymine dimers. Thymine dimer. Example. UV. Okay. That's the summary. That makes more sense than all these words here. Ionizing. Oh, one thing you may want to, I think I should write it down. Ionizing. It is also called, sometimes it's also called cold sterilization. Cold sterilization. Anything that is heat labile, you can use this to sterilize that. For heat labile materials. Anything that's heat labile, you can zap it with X-rays and gamma rays. Okay. Destroy DNA. Okay. What is the mode of action? They say they split molecules into atoms. That is the process of oxidation, actually. Okay. Loss of ions. Okay. Gamma rays, X-rays. Non-ionizing. Okay. Rather than ionize molecules, they excite, damage the molecules, cause thymine dimerization. Low energy content, blah, blah, blah. Must be directly exposed because they don't have penetrating power. Stick with what I have on the board. Forget about all this. Okay. Filtration, last physical agent. Filtration. Microbistatic or microbicidal? Is filtration microbicidal or microbistatic? Neither. It's a trick question. Yeah. When you filter something, you're not killing it, you're not stopping it, you're physically removing it. So it's neither. Filtration is neither static nor cidal. It is in its own category. Okay. Again, if something is heat labile, this is your another choice. But this is for small quantities of liquid only. You cannot use filtration for humongous quantities of liquids. You cannot clean anything that is, if you want to sterilize this pen, cannot sterilize this pen through filtration. This is only for small quantities of liquids. Okay? And you have to use a special size filter. Okay? And this type of filter is called membrane filter. Okay? Please memorize both sides. Okay? Red one and yellow one. The red one is the one that accomplishes sterilization. Pardon me. 0.01 micrometer, because this is the one that removes even the smallest viruses, 0.01 micrometer. But the yellow one, 0.22 micrometer, will only remove bacteria but not the viruses. 0.01 micrometer will remove the viruses. And once you have removed viruses, you have accomplished sterilization. But 0.22 micrometer will remove bacteria that is clean but not sterile. Okay? My overhead of somehow I skipped HEPA filters, which is not in, I don't believe I have. Yeah, this is membrane filter, as you can see. And yeah, the top chamber, here's the membrane filter. You pour your liquids, and then you must use vacuum. Without vacuum, you can sit for days for your liquid to come through. Then you must use a vacuum to pull your liquid through.
Quick question. Going back, you said you can't do large amounts of liquid.
Yep.
You said you can't. Why not?
We don't have large enough filters. Like you want to filter the whole community water supply. That's what I'm thinking. Yeah.
Okay, so it's just it's for mechanical reasons. They have
Exactly.
a filter big enough for a system of filters. But
Exactly.
it could be. I mean, you could, if you had a system, you could do a large amount of filters.
They have not made filters large enough yet. Yes. Maybe in the future they could do that. Yeah. But yeah, at this time we just don't have that large enough filters. Yeah. Maybe for home use, possible. Yeah. But what I'm thinking, like the whole city system and all that. Yeah. For home filter, I know, like for Brera and all these kind of things. For home use, they do have these kind of. But on a larger scale, like city or maybe.
Most of those are the same concept of derivatives.
Exactly. Yeah. Yeah. All right. Next one. No. So I don't have HEPA. You have HEPA filter in your notes. HEPA filter does not accomplish sterilization, but they are excellent to remove particulate matter, solid particles from air. They do remove 99.9% of the solid particles from air. Excellent, but not 100%. That's why they are not sterilant. Okay, people who are allergic to different materials, pollen, not dust, but dust mite, poop, or anything else, must use HEPA filters at home. Air purifiers, they come with HEPA filters. New vacuums, almost all vacuums, they have HEPA filters. Excellent. Okay, they work really good. Hospitals with burn units, all the air that comes in, okay, they should go through the HEPA filters. If you have a chance to visit CDC in Atlanta, Center for Disease Control, they work with all these infectious agents, Ebola virus, and all the other pathogens, polio and all that. They do research. And if you see them, they have these spacesuits on, okay, when they work, just like astronauts, and all the air that goes through several layers of HEPA filters, and then comes in, goes through several layers of HEPA filters. Okay, make sure these infectious agents do not leave their research facility. Okay, but this is not sterilant. Okay, and of course there are other mechanisms. Okay, incineration and all that in process before the air escapes. Okay. Now let's talk about, done with the physical agents, the chemical agents that are commonly used in everyday life, like alcohol, iodine, chlorine, and so on. Before we do that, we are going to go through the terminologies that is associated with these chemicals and the characteristics of an ideal chemical. Okay. what are some of the good characteristics of a chemical that is effective against microorganisms? A good antimicrobial agent should be broad spectrum. Broad spectrum meaning it should be effective against gram-positive, gram-negative, acid-fast, and all different types of microorganisms at low concentration. Solubility. Antimicrobial agents that you buy at convenience store. When was the last time that you bought a 50-gallon jug? Never. You always buy them in concentrated form, right? Mr. Clean or whatever, and when you come home, you pour a few spoons or whatever quantity in liquid, and then you use it. Okay? Why do they sell them in concentrated form? For the ease of storage, okay? So they don't have to carry literally tons and tons of gallons. Ease of storage, ease of transportation, okay? So material that you buy must be soluble in water, okay, and other solvents for the ease of application. So solubility is important. Number 2, lack of toxicity. It should not harm you or your pets or the material safety we are coming up. Lysol that we use is one of the very effective antimicrobial agents. It does kill 99.9% of the microorganism household germs. But if you have pets, you have to be very careful, especially birds, if you have your birds at home. Swiffer, I don't know. I'm not talking about the Swiffer pad that we use, but if you use liquids with the Swiffer, it is very harmful to cats and dogs. Make sure they don't lick the Swiffer liquid. It could be lethal to your pets. Swiffer liquid, okay? And birds, if you have birds, make sure that when you use Lysol at home, your birds don't get high on that, okay? It could be very, very, very harmful to your birds. Stability. It simply means it should not lose its effectiveness. It should have longer shelf life, okay? One simple example, like iodine, okay? They sell iodine in amber bottles, not clear bottles, right? Why? It is photoreactive. If you keep it in light, it will lose its effectiveness, all right? Minimum inactivation by extraneous material. I think we talked about this last time about vomit. Vomit, no? Yeah, potato chunks and all that. So if you apply an antimicrobial agent, it should only react with microorganism. It should not react with extraneous organic material. That's what it's saying. And I think last one is, no, 2 more. Material safety and price, yeah. Availability. It should be, if it is good, everyone should be able to afford it. If it is good and you cannot buy it, what's the idea? Like, for example, Cepacol is one of the good mouthwash. But not everybody can afford it. Cepacol. Okay, yeah. And finally, material safety. When you apply it, like bleach is one of the very good one, antimicrobial agent, but you can't use it on your black jeans, right? You have to use common sense where and how you can use it. I always tell this story to my students. I'm kind of eBay junkie. I buy lots of stuff from eBay, and 2 a.m. the infomercials I watch and buy lots of junk, okay? And I'm very handy too. I do a lot of work at home, like remodeling bathroom and things like that. So a few years ago, I remodeled my bathroom, gutted, put new tubs and new fixtures and everything. And then I'm watching this, I'm tired and watching, they show you this very ugly bathroom, and then this infomercial is about Zap. They zap it, and bing, everything is clean and new. Now remember, I have just remodeled my bathroom, and there's no need for me to buy Zap, okay? But let's buy Zap, okay? So we bought Zap, okay? And said, okay, I'm going to make these fixtures that I just put in, they are brand new, so I'm going to make them more shiny, okay? So, and we, the men, we don't read instructions. So we know already everything. So Zap came in, I sprayed Zap on the beautiful brand new fixtures in the bathroom. It ate up all the chrome, and I have the ugliest fixture. Yeah. So I always remind myself, right here, you should not do that. You should read the instruction, okay? Yeah. All righty. Material safety. Okay. Major groups of chemical agents now. Let's look at specific chemicals. Which do you think is the oldest antimicrobial agent? First chemical that was used, remember? Hand washing? Phenol, very good, very good. Yeah. Hand washing, aseptic surgery, Joseph Lister. Joseph Lister is the one who came up with the idea of hand washing. So the first chemical was phenol. Phenol. Okay. Same phenol, because it is so good, it really is very good chemical. It is so good that if you come up with a new chemical today, you still have to use phenol as your standard to compare your other chemical, the effectiveness of the new chemical against phenol. If your chemical good or not, you have to use phenol to compare the effectiveness of the new chemical. But the problem is we don't use the same phenol on our hands that Joseph Lister used. Two reasons we don't use it. It smells bad, okay, stinky. And number two, it irritates skin, okay. And third, and valid reason is we have better chemically modified forms of phenol available. So why use the same phenol, okay? Come on. Okay. So first of all, it is caustic, irritating. It has replaced by other derivatives like Lysol that we use. It's a derivative of phenol. The phenol or Clarasol that we use on our skin, that is a derivative of phenol, modified version of the phenol. Okay. This derivative, yeah, this is kind of sad. There was another chemical modified version of phenol called hexachlorophene. Okay. This chemical had been used extensively in the United States until 1972. This was one of the ingredients in the soap that was used to bathe all the babies that were born in the United States until 1972. But now, you know, they found out that it causes what? Nerve damage. So all those babies that you see they are walking around with, I'm just kidding. But they don't do that. That soap has been banned. They don't use this in the soap anymore. So, but sometimes we find out, they tell us, okay, use it, it's good. And then 50 years later, then they find out, no, don't use it. Okay, so, yeah. Well, yeah, like these artificial sweetener and all that. My personal opinion, don't use anything that's artificial. Stick with natural things. All this diet and all that, stay away. If the nature didn't make it, don't use it. Like artificial, all these alternate NutraSweets and all these artificial butter things like that. You know, what is, if it's not butter, blah, blah, blah. No, eat real butter, but eat less. That's it. Yeah. So, really, what is this diet thing? Full-size pizza with Diet Coke? Come on, give me a break, please. Okay. No. Oh, okay. All right. didn't want to offend anybody, please, but yeah, just my personal opinion. Do whatever you want to do. Okay. Phenolic derivatives. Okay. Are they antiseptic or are they derivative? Okay. Sometimes I just talk too much. All right. Yeah. 1% or lower, you can apply it on your skin. They are antiseptic. 2% or higher, you can use them as disinfectant. Okay. Everybody remember the difference between antiseptic and disinfectant. Antiseptic, that can be used on living tissue. If you want to mop your floor or clean your tabletop, 2% or higher, you can use them. Disinfectant. All right. Bactericidal or static. What is their mode of action? High concentration, 2% or high concentration. They function how? By denaturing or disrupting cell membrane. They will kill microorganisms. In low concentration, 1% or lower, only certain enzymes are inactivated. Okay, one more time. High concentration, 2% or higher. They will probably be cidal. Okay? Function by denaturing, disrupting cell membrane. If the cell membrane is disrupted, the cell is probably killed. 1% or lower concentrations, some of the enzymes are inactivated, so this is probably static. Static. Okay. Come on. Please. Okay. Yeah. So this is what it's saying, repeating the same thing here. Maybe static or maybe cidal, depending on the concentration. So 2% is probably cidal, 1% is static, but they are never sterilant because they cannot destroy spores. They are either cidal or static, but not sterilant. I'm going to stop here today, so give you a chance, those of you who have not taken midterm, to brush up on your studies a little bit, and we'll continue next time. Okay? Good day. Have a safe break. Thank you. Pardon me?
Is Listerine in it for that's,
Listerine, in my opinion, I've been testing it for a very long time. It doesn't work.
I mean, it's named after Listerine.
Lister, yeah.
He didn't.
He has nothing to do with Listerine. He is turning upside down in his grave. Doesn't work. Yeah.